Hello everyone. I want to take this opportunity to go through some of the Chapter 2 notes, which here we're dealing with Chapter 2, Section 1. We're just introducing here this idea of set theory. So this is actually Section 2.1. And set theory, this is a very interesting idea from mathematics. It hasn't been around really for that long if you think about in the grand scheme of things. You know, geometry or some of this stuff has been around for thousands of years. Set theory, it was invented around like 1850 or kind of like 1880-ish. It was in development, especially by this guy. He's called Cantor, Georg Cantor. He's a German guy, so I'm wondering, yeah, Georg, it sounds Georg Cantor. It's not a proper German pronunciation for this name. It is kind of an odd name for it to be German anyways, but we will get into some of these ideas of set theories. It's not really too complicated. We're going to be talking about mostly, especially in this section, we are talking about just some of the terminology that we will use. That's why we're calling it the language of sets, because here we just want to talk about some of the words that we use, some of the phrases and stuff whenever we're defining a set or when we're talking about set theory in general. We have, of course, sets, which here a set is just a group of objects in general here, or else a collection of objects. It's used with these curly brackets, which this is supposed to be a curly bracket or a curly brace. You put a set inside of here and it's just a list of stuff in the set. This would be something that's called set builder notation. We'll get into some of these kinds of terms. And then an element would be one of the things that's in here. So if you have a list of maybe colors like green, blue, red, this would be a set. It's a set of some of the colors, and each one of these individual colors, like here just the one green, is an element of this set. And sets, you know, could be given a name, like the set C. C just comes to mind like color. This would be the set that goes green, blue, and red. And we can define sets in as many ways as we want. And so we can make, for example, another set that's called C. This time C standing for carnivorous. And we have, of course, the ubiquitous curly bracket that's there, which is telling us where our set is. And if we have this kind of an equation, or any kind of an expression that has a set in there, there is a proper way that we would pronounce all of these symbols, just like we would pronounce this thing 2 plus 3 equals 5. We would pronounce this thing in a certain way. We would go C is the set of all the elements X such that X is a carnivorous animal. And so we end up saying here basically what the elements of the set are, and then when we go such that with this colon here, we're able to give a definition of how we want these elements X to appear, or how we're going to define which sets or which elements should be in the set and which ones should not be. And then it raises this question of whether a set is well defined or not, because you can give a definition of which type of, in this case it was animals in the set before. We had this kind of a set that had the carnivorous animals, set of all X such that X is carnivorous, and it should be also animal, because you know there are some carnivorous plants and things like this that are so interesting. But well defined means that when you see the definition for the set, it's clear what should be in there, and it should also be clear what is not in there. And so I wonder about with this one, a carnivorous animal, is it clear what's going to be in this set? Or in other words, if two different people set about to list everything in this set, are we confident that they would get the exact same list? If so, then we would say that it's well defined. There should be no question about, this thing, should it be in there, should it not be in there? The definition, if it is well defined, then the definition should be clear enough that we don't have to wonder about it, whether something should be in there or not. But a carnivorous animal, I wonder how do you define it? Because probably a cat, for example, would a cat be in there? Or actually, what I would like to write instead, getting us used to some of these kinds of terminologies, should a cat be an element of this set C? This little symbol, it's like an E kind of, or an epsilon or something. This means is an element of, or else you could also think of it is contained inside of this one. Is cat an element of this set? Are cats carnivorous? I think some of them are. But if you read the label on a cat food, man, there's a lot of stuff in there that's not meat. I wonder, carnivorous animal, is it clear enough what it means, carnivorous animal? Should a carnivorous animal eat exclusively meat? If so, then there's some animals that could be carnivorous that maybe are not all the time, you know, like a cat, for example. I've had a cat before that liked to eat corn on the cob, and so does that mean that cats are not carnivorous because a particular cat likes corn on the cob? Or, you know, some people might be carnivorous by choice, by eating only meat. So you might have a guy named Bob in this set or something if Bob has chosen to be a carnivorous animal. I don't know. So this one, I would say this set probably is not well defined. It doesn't feel well defined to me, this set. But I would be interested for your feedback. Is this a well defined set or not? If it's not, then we should be able to come up with maybe a reason why. Here we'll see some that it should be more clear. If you make a set of all the elements X such that X is a winner of an Academy Award, it's clear, you know, we could go back into the catalog of all the previous Academy Awards since they began, and we would have a distinct list of every person who has won an award, an Academy Award, and so there would be no question about so-and-so belongs in here, so-and-so does not. You simply must find out if they've ever won an Academy Award. But if we make a set like this, set T is going to be the set of all X such that X is tall. It makes a problem because probably a lot of people do not agree on what it means to be tall. It depends also maybe what we're talking about, things that are tall. If a tree is tall, for example, maybe for a tree to be tall, it should be at least 100 feet tall or something. Or if a building is tall versus a person, or maybe like a child, you know, if a child is tall, a child can be tall while being shorter than an adult. And it makes all of these questions, like, what are you talking about tall? What does it mean tall? Tall is basically an opinion, whether something is tall or not. You know, tallness is in the eye of the beholder, as they say. And so, this would not be a well-defined. This one is. It is well-defined. This other one over here is not well-defined. And so, we will see, of course, a description about Academy Award winners and whether or not somebody is tall. But moving on, we have another symbol that we'd like to introduce. And so we had before these symbols, the open and closed curly brace, which just denote a set. Notice something about this set. It's got the open and closed curly brace, and so it's a set, but then what is inside of the set? Do you agree that there's nothing inside of this set? There are no elements for sure. And so if a set has no elements, it's called an empty set, or else null set. Seems empty set sounds better to my ear, the empty set. And the empty set also sometimes is given this other symbol, which is either a 0 with a cross through it, or else it's some type of a stylized Greek letter phi. It could be seen as that one, I guess. But these are the same. Having an open and closed curly brace with nothing inside, or else just using this symbol, which if you see it as a Greek letter phi or phi, however you pronounce this one, then we're just using that letter to represent always the empty set. Now, speaking of an empty set, we'd like to answer this question. It's kind of a fun one to think about. With these symbols together, a set like this, how could you describe what this set is? Notice if we wanted to use our little terminology that we have of how we can name this open curly bracket, we say the set. We could say the set with the empty set as an element. And so this one actually here, this one is a set. It's also an element of this set, a set that has the empty set in there. And it's possible for anything at all. That was kind of what we were talking about at the beginning a little bit, that a set is a very broad term. It just means a collection of things or items, a collection of elements. There's no limit on what the elements could be. And so, of course, it's allowed that elements of a set could be other sets. And so here, since the empty set is a proper set, there's nothing wrong with saying that that's a set. It's actually the empty set. There's no reason why that cannot be the element of a set. And so it would actually have a distinct meaning from just this symbol, because this symbol means the empty set. This symbol means a set that has the empty set as an element. And so this thing has one element, whereas the empty set over here has no elements. And so we would say that these are not the same thing. And then we have also this idea of having, some people actually write their zeros like this, and so I don't want it to be confusing based on the handwriting. But this set over here, of course, like we've been talking about, it is a set that has a set as an element. This set over here with the 0 inside, that would be a set that has a number as an element, the number 0. So these would be different, not to get them confused. And then we have another little symbol that we're going to use. It doesn't have to be U all of the time, but it makes sense to use the letter U. It's going to stand for the universal set. And basically the universal set, it will be the largest set that you can consider based on what you're talking about. So what the universal set is, it can change based on the context. For example, this set A, where it was all of the people that have won an Academy Award, has won an Academy Award. In this case, the universal set probably would be what? It should be the biggest set that we can consider out of all this. And we're basically choosing elements out of that set to be in here. I feel like it would be all actors. Maybe the universal set in this kind of a circumstance. It could either be a set of all the people on Earth, but we're not really talking about people on Earth necessarily. We're mostly talking about actors. So the universal set would be the set of all X such that X is an actor. That would be a universal set, and I mean to use curly brace. We could even come up with, why not? I'm going to come up with a different universal set for this one, because the universal set here, since we didn't define it, of course, you can define, or else the universal set will be defined for you in each different kind of a circumstance so that we're not trying to guess. But also, what about set of all X such that X is just a person? Because any person at all is liable to win an Academy Award. Of course, you have to be an actor first. That's why I feel like this universal set, that's just all actors, it makes more sense for this kind of a circumstance. But here, we can have an example of a universal set where if we're talking about female consumers living in the United States as our universal set, then we can make some subsets of this one, like based on demographics or whatever. Now, we saw before a little preview of using this symbol, which means it's an element of. Most of the time what we'll see in these math classes and these different topics that we're talking about, like set theory or the logic or something like that, if you just draw a slash through something, it means the opposite. So just like equals and not equals something, 0 is not equal to 1. We will go like this one. And so we're using the intuitive kind of a version of that. So here for these ones, replace the symbol pound, or hashtag if you like, or the number symbol. We're going to give it a shot. Replacing it with the proper thing of is an element or is not an element of. What about, here the number 3. Is the number 3 an element of this set? I see it over here, so it should go is an element. What about, this is kind of maybe a little bit of a tricky one. You notice this is saying the set with 5 in there. Is that an element of this set? Well, this set does not have sets inside, it has numbers inside. And so to say that a set would be the contained in there would not be correct. We should have such a situation like this, 2, 3, 4, and then maybe the set with 5 in there. You see, this would be different. And then the set with 5 in there would be an element of this set altogether. But it's not an element of the one that we have there, so we'd say is not an element of. But anyways, you can see what would be the proper ones there. And then we have something that we will be using as well, this idea of a cardinal number. Cardinal, it should have some different definitions, this idea of cardinal, but the cardinal number is speaking about a size. The cardinal number of a set is the size of the set. I will put size in quotations because what do you mean by size? Size of a set is basically how many elements are in there. It's the number of elements. And so there's a lot of study about cardinal numbers. There are, actually, this might be a fun fact, there are different kinds of infinity. Here, we're talking about finite sets versus infinite sets. A finite set means that the cardinal number, how many elements are in there, is just a number like 5 or 10 or 1 million or a billion or something like that. An infinite set is a set that you cannot say how many elements are in there. There's no such number that you can say because an infinite set actually will always have more elements than any given number that you can pronounce. Like a billion, well, there would be more than a billion. And if you say the biggest number you can think of, there should be more than that if a set is infinite. And so we can talk a little bit in the future about this idea of infinite set. There are actually different kinds of infinity, and this is an idea that came about basically through the study of set theory, that it's not sufficient to just say that infinity is such a thing, because some infinities are bigger than others, and I hope that we'll have a chance to expound on that a little bit. But it's outside of the bounds of just the 2.1. And so here we're thinking about finite versus infinite. P is this set of all x such that x is a planet. We would say that it's certainly finite. Of course, what the cardinal number is of P, which, by the way, you write in P, this is how many elements are in there. I think this number keeps on changing all the time, doesn't it? Like every 5 months, somebody decides that there's a different number of planets in our solar system. But surely, there should be, how many are there? How many planets in the solar system? Can you think of them? Mercury, Venus. You know, men are from Mars and women are from Venus. We must be up to 4 by now. And then there are these planets, these kind of like outer planets, these gas giants and so forth. And then there's Pluto. Isn't Pluto so lonely because people cannot decide if he's a planet or not? And so it causes him identity issues. But we'll say that it's a question mark. Maybe there's like, it's approximately somewhere between 8 or 9. 8 or 9, maybe. How many do you think? It's up to you. What about this set? This is giving us a little preview. This is an infinite set, of course, because it's just all the numbers like 1, 2, 3 going up. This would be the set. It's called natural numbers, these numbers. Natural numbers, or else counting numbers. There is no limit to them. They just keep on going forever, and so they're infinite, of course. And then we have some of these other ones. What about the empty set? Is it finite? Finite would mean you can tell how many numbers are in there, or how many elements are in there, and since there are no elements, the cardinal number for the empty set, which there I drew it kind of backwards, but the cardinal number is 0. There are no elements inside of there, so it's not a problem. We would still say it's finite, though. And then we have some little solutions for these, and that does it for 2.1. I really appreciate it if you guys were able to stick through it with this video. There will be the 2.2 notes coming up, of course, and I would like to take a look, especially if you guys have any questions about them, at any of the homework problems for these sets. And we could see some solutions for those as well. But anyways, I will catch you guys in the next video. Bye.